Imagine you own a warehouse, a massive, ridiculously expensive warehouse, the size of 3 football fields, just to store your stuff. Now imagine someone walks in, hands you a magic algorithm, and says, "Hey, you can fit everything in a garden shed now. Same stuff, zero loss. Oh, and it's 6 times cheaper to run." You'd call that person a genius, or a liar, or both. Well, Google just did exactly that to the entire AI industry. On March 24, 2026, Google Research quietly dropped a paper called TurboQuant, and within 24 hours, memory chip stocks were in free fall. Samsung down, SK Hynix down, Micron down, SanDisk down. The market panicked. Why? Because TurboQuant doesn't just improve AI, it potentially rewrites the economics of AI forever. And today, we're going to break down exactly what it does, how it works, and why it matters to you, even if you've never written a single line of code in your life. Buckle up. This one's a big deal. The problem: AI is a memory hog. Let's start with the problem, because to understand why TurboQuant is such a big deal, you need to understand just how absurdly memory-hungry modern AI has become. When you chat with an AI, whether it's Gemini, ChatGPT, or anything else, the model doesn't just read your message and respond. It has to remember everything. Every word, every sentence, every token in the conversation. It stores all of that in something called the KV cache, short for key value cache. Think of it like a waiter's notepad. Every time you add something to your order, he writes it down. Now imagine a dinner that lasts 6 hours with 200 courses. That notepad becomes a novel, and the waiter needs a bigger and bigger pocket to carry it. In AI terms, that pocket is GPU memory, and it's brutally expensive. We're talking about high-bandwidth memory chips that cost thousands of dollars per unit. And as AI models get smarter and handle longer conversations, what the industry calls long context windows, the KV cache explodes in size. For a 70 billion parameter model processing 100,000 tokens, you're looking at over 150 gigabytes of memory. That's not one GPU, that's 7 high-end RTX 4090 graphics cards, just to run a single conversation. This is the bottleneck that's been quietly strangling the AI industry. More memory means more hardware. More hardware means more cost. More cost means AI stays expensive, stays in the cloud, stays out of reach for most people and most businesses. Until now. Google's TurboQuant is, at its core, a compression algorithm. But calling it just a compression algorithm is like calling the Apollo 11 rocket just a firework. Here's what it actually does. It takes that massive KV cache, all those high-precision floating-point numbers stored at 16 or 32 bits each, and compresses them down to just 3 bits. 3 bits! That's a 6x reduction in memory. And here's the jaw-dropping part. It does this with zero accuracy loss. None. The AI performs identical to the uncompressed version. And it gets better. On NVIDIA H100 GPUs, the gold standard of AI hardware, TurboQuant delivers up to an 8x speedup in computing attention. That's the core calculation that makes AI think. 8 times faster, at a fraction of the memory cost. Now, you might be thinking, compression algorithms have existed for decades. What's so special about this one? Great question, and the answer is in the details, because this is where TurboQuant is genuinely mathematically elegant. How it actually works, the clever math. Most compression methods have a dirty little secret. When they compress data, they must store extra information called quantization constants, so the system knows how to decompress it later. These constants add 1 to 2 extra bits per number, which sounds small until you realize it partially cancels out the compression you just did. You're robbing Peter to pay Paul. Well, Google just did exactly that, with 2 brilliant tricks.
Trick number 1, PolarQuant, changing the map. Imagine giving someone directions. You could say go 3 blocks east, then 4 blocks north. That's Cartesian coordinates, and that's how AI normally stores data. Or you could say go 5 blocks at a 37-degree angle. That's polar coordinates. It's the same destination, but for this kind of data, it's far more efficient. PolarQuant converts data vectors into polar form, a radius, which represents signal strength, and a set of angles, which represent direction. Then the system applies a random rotation. After that rotation, the angles fall into a highly predictable pattern. And here's the key point. The system already knows the overall shape of the data. Because of that, it no longer needs to store expensive normalization constants. The bookkeeping disappears. The overhead vanishes completely. Now, trick number 2, QJL, the one-bit error eraser. Even after PolarQuant, a tiny residual error remains. In most systems, that error doesn't stay tiny, it accumulates. Over long contexts, it can distort attention and eventually show up as hallucinations or wrong answers. TurboQuant fixes this with QJL, the quantized Johnson-Lindenstrand transform, using just one single bit per number, a plus or a minus. That's it. This one-bit correction removes bias entirely, so the errors don't drift in one direction. Statistically, the AI's attention scores stay identical to the full precision original. 2 stages, 0 overhead, near perfect accuracy. That combination is why this paper is being presented at ICLR 2026, one of the most prestigious AI conferences in the world. Now let's talk about the benchmarks, because claims like this need proof. Google tested TurboQuant across 5 major evaluations: long bench, needle in a haystack, zero scrolls, ruler, and L-eval, using models like Llama 3.1, Gemma, and Mistral. Needle in a haystack is brutal. The task is to find one specific sentence hidden inside 100,000 words, like a grain of sand on a beach. At 3.5 bits, TurboQuant achieved 100% perfect recall across context lengths from 4,000 to 104,000 tokens, no degradation at all. On long bench, which covers question answering, code generation, and summarization, TurboQuant matched the full precision baseline exactly. The score was 50.06 versus 50.06, identical. For vector search, the technology behind Google search, YouTube recommendations, and advertising, TurboQuant outperformed every state-of-the-art competitor, including PQ and RobbieQ, while adding virtually no indexing time. The community response was immediate. Within 24 hours, developers ported TurboQuant to Apple Silicon using MLX. One developer tested a 35 billion parameter model at 64,000 tokens and reported a 100% exact match at every compression level. So what does this actually mean in the real world? For enterprises running AI in production, TurboQuant can cut GPU costs by 50% or more. There's no retraining and no fine-tuning. You apply it to your existing model, and it works today. For developers, models that once required cloud clusters can now run locally. A 70 billion parameter model that needed 7 RTX 4090s at 100,000 tokens can drop to 6, and the savings keep growing as compression increases. For regular users, this is how powerful AI ends up on your laptop, your phone, and your edge devices without your data being shipped off to a server farm in Oregon. And here's what the market initially missed. This isn't a threat to hardware demand, it's a multiplier. Cheaper AI means more people run it, more applications become viable, and more models stay active. The pie gets bigger, not smaller. As Morgan Stanley's head of Asia Tech Research put it, TurboQuant isn't about incremental optimization, it's about shifting the cost curve of AI deployment. That brings us to the bigger picture. Most compression methods are engineering hacks. They work, but they aren't provably optimal. TurboQuant is different. It operates near the information-theoretic lower bound, approaching the mathematical limit of how much this data can be compressed without losing information. You can't do much better without changing the physics of information itself. That's not just engineering, that's mathematics, and it signals a turning point. The era of throwing more hardware at the problem is ending. The next phase of AI will be won by elegant algorithms, not the biggest GPU clusters. Google just fired the opening shot. Remember that warehouse from the beginning, the one that shrank to a garden shed? That's not a metaphor anymore.
That's TurboQuant, and it's already changing the economics of AI everywhere.